Hello and welcome back to a new video, D3D12Ez, here on the Ludwig Fusel channel. Now in the last videos what we have done is we have uploaded a texture to the GPU. We loaded it with the Windows imaging component and we uploaded it with DirectX 12 and now it's ready on the GPU, but if we start the application, of course it's not there because our shaders do not employ a texture at all. Our whole pipeline does not accept a texture and that's what we want to change in this video today. So if we're gonna get through everything as fast as I think, we might already see the texture on our triangle today. So how are we going to do that? Well, it's actually not even that hard. So what do we need to do to get the texture running on the GPU? Well, actually we need to do two things, or two major things. First of all, we need to change our render paths on the GPU. So we need to change our shaders so that they reflect the usage of a texture in general, because a shader is, as I always told you, it's kind of like a static thing. It's just an algorithm, but it's not bound to any certain data. In a shader you can write everything, right? In this case here we just composed the color out of a static color from a register that was set at execution, one color for the whole triangle, and in the vertex shader we also basically just passed on some coordinates that came in from the data. So basically what we do with shaders, with the root signature, with our input assembler layout and all of that things, we basically just describe a way of how our GPU operates. And then what we do on the CPU side or on the C++ side is we dynamically set this data. We control and we use the DirectX 12 API to upload the data to the GPU, to transition the data into multiple states and to keep it in the right location and in the right setup with all of the features that we have used until now to basically add the dynamic data for the shader's execution, for the render path's execution. So if we want to add a texture to the triangle, we need to now, in this video, change two things. We need to change the shaders and we need to change our C++ runtime. Now let's start with the shaders, because this is kind of like the thing that we now gonna have our main focus on. Okay, actually not, we might have switch for focus in the future as well again, but in general where we want to end with that, and so as well as if we are transitioning to real-time rendering, we always gotta have our focus on the shaders because the shaders matter. Of course the API also matters, but that's something that I don't want to focus too much in the tutorial series from now on. But we're still gonna explain how things works, of course. Alright, so how do we alter the shader so that we can employ a texture? Well, in general, the vertex shader, it's only used for geometry manipulation. So for the color values, the geometry shader is not really useful. So what we're going to use is the pixel shader. The pixel shader here is used for coloring the pixels, which we have done here with a color from the register. So basically what we want to do is we want to change that color that's currently coming here from this register, from that basically that static data set at execution. In the root signature, we want to change that to a texture. Now, how can we change that to a texture? Well, we need to do multiple things. First of all, we need to define how the texture is bound. So we need to bind the texture to a register similar to what we have done here with the float 3 for the color. We need to bind this to a certain register, and then what we need to do is we need to use it or define it in here like we have done it with the color, just as the texture, and then we can use it inside of here. Now, how do we do that? Well, basically what we're going to do is we're going to alter our root signature. And now since we are using a texture, we are getting into a bit more involved usage of root signatures. And to get use of them, I've actually already prepared some documents on the internet, specifying root signatures here on the Microsoft documentation with nice visualizations how these root signatures work. Now, this is basically the root signature here on the left on that image. And what we have used for the root signature is what is seen here under 5, which is the uint bound to B9. Well, basically what we have done, we also use the uint, but we haven't bound it to B9, we have bound it to B0, and we also aliased it with a float. Oh, that's the wrong IDE, there we go. And you can see buffer 0, and we have aliased that because 3 32-bit constants, 3 32-bit uints, we have aliased that in the shader to a float 3, which is totally valid because we're just reinterpreting the data differently from memory or from the root signature, which is basically a certain portion of memory on the GPU. And we reinterpreted this as a float 3. Now, this is basically what we got. And now what we want to do is we want to get into these advanced features. Now, how do these advanced features work? Well, the advanced features basically work by putting descriptors on the root signature or referencing descriptors from the root signature. Now, these examples here, 0, 1, and 2, these are descriptors on the root signature, and 3, 4, and 6 are references to descriptors somewhere else in memory on the GPU. Now what you can put on there are multiple things. You can put in CBVs, SRVs, and URVs. And what you can do is you also can put in samplers. But samplers are a certain special way. I'm gonna ignore the samplers for now. We're gonna get to them later in this video. Now currently I just want to take a look at CBV, SRV, and UAV. These are so-called views, and views are actually a certain kind of descriptor on the 3D12, and these are descriptors that live on a descriptor heap on the GPU, or actually they can live on a descriptor heap on the GPU. Now the very easy and straightforward use case is to just put them in the root signature. You can do that with CBVs, SRVs, and UAVs. It always works. You can always put them in here. They might have a bit of reduced features, but most of the time they are as good as descriptors that are not in kind of like a descriptor heap and outside of the root signature. Now the only consideration is actually the size of the root signature and if you want to use some of these advanced features. In general, I would not recommend to put certain kinds of descriptors on the root signature. It's good if you just have something that's just there once, like one texture, one kind of static data that you access, one unordered access view that you are using. If you're using like one of these and just only one and you never want to add more than one of these, then it's totally valid to put them inside of the root signature itself. But as soon as you have two or more, you're gonna put it outside of the root signature. Now, what are these things? CBV, SRV, and UAV. These are constant buffer views, shader resource views, and unordered access views. Unordered access view is something special, especially useful for like compute shaders and things like that. I don't want to get into too much details what they are. I want to get into the details of constant buffer views and shader resource views. Constant buffer views is basically a descriptor to a so-called constant buffer. A constant buffer is basically just any arbitrary data on the GPU. Any arbitrary collection of uints, floats, matrices, vectors, like everything, like just like a struct, right? It's basically a struct on the GPU or an array of struct. One single constant buffer view can be like an array of structs, an unbound array, and there can be many aliasing things going on the GPU, but basically constant buffer is just a struct on the GPU. Now what we also have is the so-called shader resource views. Shader resource views are at the end of the day, the same than a constant buffer view, some arbitrary data, or not like a constant buffer view, but like a constant buffer, arbitrary data on the GPU. However, these are used as shader resources. So actually, while the constant buffer is kind of like directly accessing the members of the data, the shader resource view has kind of like a proxy in between, a middleware that manages access to the data because it's actually a so-called shader resource. Shader resources are, for example, textures, or most of the time going to be textures. Now, basically what these proxies is going to do, it is going to make the access to the texture way simpler, because as I told you, textures are not that simple. When we described the texture in D3D12 on the CPU, it was actually quite hard to describe it because we had like this the dimension, then we had like mip mapping that we needed to fill in, multi-sampling and things like that. So basically shader resource views can be very, very complex. There can be like multiple resolutions on the GPU. The resolution may vary based on the resolution that's dynamically selected. You can actually normalize the access to the textures by providing coordinates between 0 and 1 that then automatically gonna be mapped to the range of 0 to n-1 pixels that are actually in the texture. And there are like many things that are automatically done and managed for you on the shader resource view. Because as we already have used on the GPU, it was always normalized between -1 and 1 or between 0 and 1. This is always normalized. And if you're working on a GPU, you're always going to work like in a normalized way, and then you're applying some correction to put it kind of like in the space of the display of the monitor. And this is why we have the shader resource views, because we basically need to map from something normalized to an access to an actually memory location, like kind of like the index of a pixel inside a data buffer, which the data buffer, the resource that is behind of it, is actually already created as a texture, and so is kind of like placed at the right memory location so that it can be accessed by that middleware, by the data proxy. So SRV, shader resource view, is kind of like a view, a descriptor for a texture where we basically define how kind of like this texture is accessed. And this is basically what we need. Now, what you can do is you can put a shader resource view directly on the root signature. However, I don't want to do that. I want to use the so-called descriptor table. Now, what is a descriptor table? So basically, instead of directly specifying the view to the shader resource on the root signature, so basically writing out the location, kind of like the address of the data and a bit of meta information, how to access and how to kind of like configure the access to that shader resource, instead of writing that inside of the root signature and always kind of like putting it in the root signature, we're going to put it into a dedicated descriptor in its own dedicated memory that is then referenced by a descriptor table. A descriptor table is basically just a range, an array of descriptors, and the range of descriptors can have multiple types. In this case, you can see that the type of the descriptor range is CBV, UAV, and SRV. These are kind of like aliasable. You can kind of like see that the CBV, UAV, and SRV is kind of like in C, a union, or in C++, like a union. They kind of like overlap, and depending on how you use them and how you define them, the GPU knows if it's describing a constant buffer, an unordered access, or a shader resource. So this is kind of like the thing that's going on here. So basically what we do is we allocate a array of descriptors on the GPU, and we kind of like fill out this array, and instead of then on the root signature putting the plain data in here, we basically put in the address of the array. So we basically tell the GPU, all right, this is the array where all the metadata, the descriptors are stored. Why do we do that? Well, we do that because we don't know how many textures we're going to use. Of course, inside of that tutorial, and before I'm going to rewrite the whole code base, we are only going to use one texture. But I want to teach you how you can do it the proper way and how you can use the most features out of it. And the best feature, especially if you're using textures, is by using an array, because actually what you can do inside the root signature, you can define that a range has a unknown size. You can see SRV's unknown array size. So what you can actually do is you can tell the GPU that, oh, right, at this position, the textures are going to start. However, I'm not going to tell how many descriptors are in there. And this basically has the effect that you can put as many textures as you want inside of the array as you want. And then the only kind of like limitations on how this is then dealt at the runtime is that the descriptor is actually valid. If you're accessing a descriptor that's not valid or outside of the range of the heap, you're going to have a D3D12 error, the application may crash, the device might be removed, or you're just going to get like a null shader resource view that's just always 0. That depends on how it's kind of like implemented and how the spec says. But basically you shouldn't never do this. So basically what you can do, if you have a descriptor table, you're probably going to pass, for example, as a uint, the index of the texture you want to use, and then you can write in the shader, kind of like take the index that you want to use, and then kind of like indirect inside of that array of SRVs. Now you can see that the table can actually have a certain layout, so you can start with a CBV, then 2 UAVs, and then you can have an unbound number of SRVs or a bound number of SRVs. Only kind of like limitations is that as soon as you're kind of like starting an unbound range, the range is kind of like limited, and kind of like an unbound range always needs to be at the end of a table, because if it's kind of like before the table, it's no longer possible to access like the CBV. If the SRV would be above the CBV, nobody would know where the CBV starts, and so it's not possible. The same goes for these register indexes like buffer 0, U1, U2, and texture 1. As soon as you're using an unbound size, you're basically starting with like T1 in this case here, and then all subsequent Ts are kind of like allocated for that unknown array, and you can no longer use the range. So if you have multiple textures here, like one bound and then one unbound, you always need to start at T0 and then go to T1. There's also a way of aliasing this with so-called spaces. You can define multiple like spaces of counting. However, I don't want to go into too much details of that, because like spaces, they are useful, especially if you have a complex render path, but can see like buffer 0 and buffer 0 space 1 does not conflict, because by default it's like space 0. And we don't want to go too much into these details because it's too complicated for now. So what I want to do is I basically want to define the descriptor table with an unbound number of SRVs. That's basically what I want to do. And we're going to start with that by taking a look at the example. Actually, we could also take a look at the example above, because it's like the same one that we had. And then we can go inside of Visual Studio and define it. So basically what I want to do at location 0, we had kind of like the color in the root signature layout. Now at index 1, I want to have this is kind of like a descriptor table for textures. And then we also gonna have them bound here on the layout. So T0 plus or T0 dot dot is gonna be, let's maybe format this a bit different so that's looking a bit better. Maybe we don't need it here that hard of an indent. but like something like that. And this is gonna be float for textures, or texture 2D of 4-dimensional floats. This is kind of like the terminology how you're then gonna do it, which you're gonna later see that we do it like that. So now basically what I've done, I've updated my mappings, and now I of course also need to update the root signature. I need to add a comma here, and then I need to have the descriptor table defined. If I define the descriptor table, I actually want to have it defined like that, and then I can put in my entries here. So now we have a descriptor table, and now we just need to tell the GPU what's inside of the descriptor table. We're going to have shader resource views. I'm just going to copy what we've got here on the documentation. SRV, they're going to start at texture 0, and they are going to be unbound, so as many as you want, basically. So by defining it like that, we will find that we have a descriptor table with an unbound number of SRVs starting at T0. So root signature is updated. I should be able to recompile that without any issues. All right, you can see it compiles, no problems. One succeeded, the shaders were recompiled. So that's all good. And now what we need to do is we need to use the texture. How do we use the texture? Well, we go to our pixel shader and we use it. Now, of course, there's a documentation element as well. There's a so-called resource binding, and you can already see that the first example of resource binding is actually a texture. I'm going to copy that over, and then I'm going to explain you how that works after modifying that. Now, the first thing that I want to do is add a semicolon, apply the register to T0, because that's how we defined it, and rename this to textures. Now, basically what you do, the data type of a texture is called texture 2D. If you have a 1-dimensional texture, it's texture 1D. If you have a 3-dimensional texture, 3D. In our case, we have 2-dimensional texture and normal image. Other types of textures are useful, but for example, like sampling a function in a texture, or basically having like a pre-computed function stored in a 1-dimensional array as a texture 1D, because textures are differently accessed than arrays, but that's a different story. Now, texture 2D basically means normal image, and then what you need to do is you need to kind of like provide template arguments, and these template arguments are basically telling you what's the format of the texture. As you can see, if I go into my main.cpp, we had a texture that had 4 components, so R, G, B, and A. Where do we have it? How do we have the texture? Pre-committed resource. What is that texture here? That's the texture. We have we took the pixel format out of the texture data, but basically the pixel format that we have used here from the texture was basically, if you recall the old videos, were basically RGB and A, and this is why we also use RGBA, so 4 components on the GPU. And again, the texture is accessed in a normalized way. This is why it's a shader resource view and not a constant buffer. So it's not basically every pixel is not 4 UINT values. It's actually proxied. This always works with textures. It's actually proxied to a value of 4 floating points. So 4 floating points, they are normalized 0 to 1 for the actual texture values. And then we'll just give it a name. We tell it that it's in an array, and since we don't have kind of like a size of the array, I'm just going to provide like these opening and closing brackets. And if I'm not going to specify a size, it basically means unbound. And then I just say that it's going to start at register T0, and every like increment is going to be an increment to the next texture. Now what we need to do now is we need to use it. How can we get the color from the texture? So if I say like something like float 4, pixel, something, I'm just going to call it pixel because it's now coming from the texture. Or actually, since it's coming from a texture, it's actually a texel. So texel is kind of like a pixel from a texture. Pixel is kind of like a screen pixel, and texel is kind of like the pixel from a texture, if you kind of like stay at the terminology. Now what I can do now is I can go to my textures array, and since I want to just use the first texture here, I'm gonna just hardcode that. We're just gonna take the first texture, and now I need to access the texture, so we can actually press a point on there because the texture is kind of like an object, and you can see that the texture has many members available. You can provide multiple ways of getting information from the texture, like level of detail, gather alpha, blue, and there's also like red and green for all of these channels, or to get kind of like the dimension of the texture. texture, so how many pixels are in the texture. They can also do that. You can also load kind of like from the texture. If you're loading from the texture, it's kind of like loading that with a normal like integer value. But what we want to do is we want to sample the texture. Sampling is the normal way that you access a texture. And if I call the sample method, you can see that I need two more information there. I need the so-called sampler state and the location. Now the sampler state is information on how to sample the texture, kind of like a meta state, how the texture is accessed. So basically what happens if you are trying to access the texture out of range, how to filter values that are not falling into an exact pixel. So for example, if you have a texture of a even size, like 4x4 pixels, and you are trying to kind of like access the middle pixel, it's not gonna be possible because there is no middle pixel because it's 4x4, and then you basically need to interpolate between 4 pixels to get the correct value. And this is what the sampler basically controls, how that interpolation between actual pixel values happens. There's also more stuff that's going on with samplers, but I don't want to go into too much sampler madness details just yet. We're gonna see how we can define them in a second and how we can use them. But before we're gonna do that, I want to talk about the next parameter, the float to location. The location is actually the kind of like position from where to read in the texture, kind of like the coordinates from where to read from a texture. And I told you that since we are using a text and it's not like plain memory and we are sampling it, we are actually not using actual pixel constants. We actually use a normalized range between like 0 and 1. So if I want to sample the center pixel, I would hardcode a value of 0.5 in here. And that's what we're going to do for now. And I'm going to later on show you that we, of course, cannot hardcode this value, and I'm going to show you how we can provide that value. Now, the first thing that we need to fix is the sampler. Now, how do samplers work? Well, samplers are also bound on the root signature. No, there it is. There's my tab that I searched. You can see I already omitted them in my previous explanation, and you can see that we have the sampler here, and we have a static sampler there. Now, in general, samplers are just kind of like a binary description on how a texture is accessed. It has nothing to do with kind of like data that, if you would put it directly in the root signature, can be changed. This is while it's not directly in the root signature, however you define it in the root signature. If you have a static sampler that is kind of like just baked and cannot be changed at runtime, it is still defined in the root signature, but it does not count towards the indices of the root signature. This is because a static sampler basically just evaluates to a certain binary values that are just kind of like used once for setup on the GPU. It's not something that dynamically changes. It's not something that we can influence. However, what we can do if you want to change them, if we don't want to keep the sampler in one state, if we want to have it dynamically changed, we can define samplers in their own descriptor table, in their own descriptor heap on the GPU. So we have own sampler descriptors on the GPU. However, these always need to be referenced by a table because they are not static. And these can be changed at runtime. So basically, these are possible to change. There are so certain flags that you can specify on a sampler, on a non-static sampler that basically tells the GPU how they kind of like change. I don't see that they've used the flag inside of here to change them. No, they haven't used it in here. However, you can customize how frequent these samplers change, when the change might occur. Same also goes for all these descriptors. You can always like add flags that tell the GPU how the data might change. And if the data is kind of like changing in a certain way, you need to specify that, and you can basically specify this data is not changing at all. It is set once and then it's used, but it's kind of like dynamic data set by like configurations of your application that cannot be like baked into the shader, and then the GPU can optimize it as if it was a static sampler. So it could load this in a certain way that it would be faster. Works for all of these descriptors and also samplers. However, what we're going to do today is we're just going to define a static sampler. I also don't want to go too much into details how samplers work. You can define a default sampler in just one single line here, so just by the keyword static sampler and the register. There are a few things that you can actually customize here, like the addressing mode, which basically means if you are going out of the 0 and 1 range, how does the texture behave? Does it just clamp off to a so-called border color and a 0 or 1, or shall it automatically wrap so that the value again kind of like a small bit is taken by modulo 1, so it's kind of like 0, 1, and then if you're going to 2, it would be again 1. You can have it mirroring, so that kind of like goes from 1 and then from 1 to 0 again, even through you're kind of like accessing the range between 1 and 2. Or what you could also define is you could define something that's called clamping. It's shown here. If you're clamping the value, basically every value that's bigger than 1 is set automatically to 1, and everything that's kind of like less than 0 is automatically set to 0, and you kind of like have kind of like a stretching effect of the pixels, similar to that one that we have seen how our texture looked on the GPU when we uploaded it and we have not considered the alpha value for display. There's also like a filtering function, as I already told you. If you are trying to access a pixel outside of the, or if you're trying to access a pixel with these normalized coordinates between 0 and 1 that's not actually kept by a pixel or not actually served by one dedicated pixel, there need to be filtering that's need to be considered. So basically interpolating the values or not interpolating the values depending on how you specify the flag here. And maybe we're going to play a bit around in these if we get everything working. But for now, I just want to define a static sampler. Currently, we don't want to go into too much details on how these samplers work. We just want to have one static sampler that we can use. This is also specified in the root signature. So after the table, I want to have another entry. It's a static sampler. And the static sampler is going to go at slot 0 because we haven't used any sampler yet. Now, we don't need to update the CPU layout because it's a static sampler. It has nothing to do with the CPU. It's in the root signature, but it's kind of like static. It's compiled. It's not customizable. So it's only gonna occupy some spaces in here. So now we have the sampler 0, which is our sampler. And then we're just going to say for texture. So it's going to be the sampler that we use for textures. Now the next thing that we need to do is we need to bind the sampler. Now how do we bind the sampler? Well, it's actually quite easy. Just need to scroll a bit around until I find it. There is a binding of a sampler. I'm going to steal the code. We go to the pixel shader and we're just going to define it in here. They defined an array of samplers. We don't need them. We're going to call that one texture sampler, and the register is S0, so it's the sampler with number 0. And now you can see the sampler is defined in here. And now the only thing that's left to do is putting the sampler in here into that sample call, because the sample state is actually coming from the sampler, which is defined here. This is basically sample state. Now what we want to do, of course, now is we of course want to use that color value. Actually, I'm not going to use the all color values. I'm just going to use the RGB values here, not the RGBA values. It's a float 4. We only used X, Y, and Z values to kind of like extract the data. However, since a float 4 can also have like color values, RGBA is also totally valid to just extract the first 3 values here. So that's possible. You can just do it like that and get the color information from a texel. Now, if I now compile my shader, you're going to see that everything succeeds and everything is good. And you can also see that I'm going to still be able to execute my application, but you're going to see that our triangle is now completely black. Why is our triangle completely black? Well, basically because we have an issue with sampling, because the descriptor heap is not set and the descriptors are not valid. Now, if we go inside of here, we might even get a information. Do we get an information here that something is not going to go right? We might not even get the information that something is not going to go correct, because it's basically on the GPU automatically, if it's not bound, kind of like going into like a no-op state or into a special operation state. It's telling us something. The specified root signature contains at least one descriptor range, which was declared both unbound and static. Yeah, that's something different. We might need to take a look at this warning if we're going to go a bit more into the details, but I think the video is already long enough to talk about like these, how descriptors and data behaves on the GPU and how optimization works. It is actually a message just. I don't think it's even an error or warning. It's basically telling us, hey, you have to use it in a certain way without specifying kind of like more information. I am going to do something that I assume is correct as DirectX 12. However, it's not as you have specified, and it's not what kind of like the default setting would mean if you don't specify something, but I have done that. Please consider rewriting your code. That's better. But currently we should be able to just ignore that and come back to that as soon as we maybe talk about more a bit about that. Probably, maybe I'm going to do 2 more videos on D3D12Ez after that before I'm going to rewrite the whole framework, or at least, yeah, we're probably going to expand it maybe to a quad or something similar to that, so that we can play a bit more around with stuff. However, yeah, currently I'm just gonna ignore it. Maybe in not the next video, but the video after the next one. Maybe we're gonna consider it in there. Now, I told you that we might see a triangle. However, I felt that it would be a bit more beneficial if I'm going to go a bit more into the details on how the root signature works and how we can use the root signature to bind the texture in the shader and how to use the texture in the shader. I think it's more beneficial than trying to rush a colored triangle here with pixel values on the screen, or with texture texels on the screen. So yeah, thank you for watching. See you in the next video. Make sure to like and subscribe, and have a nice day. Bye.